Okay, physics. In this class, you're going to be asked to do algebraic rearrangements and to solve problems without numbers and to get to an equation. So it's not an unusual question to ask you to come up with and derive an equation, and you shouldn't be scared of that. But getting a little bit of practice with it really helps. So let me talk you through a couple of things to make sure you've got your head around this. So we're going to have a whole bunch of equations, and just rearranging those you should get some practice with and be comfortable with. So for instance, we know the electrical force is going to be what, K times the product of the two charges divided by the distance squared. So you should be comfortable solving for any single variable that's in here. So if I wanted to get to Q1, right, I would multiply both sides by r squared to get to this, and then I can divide by K and Q2 on both sides to get to my final answer, where Q1 is going to be r squared times the force divided by KQ2. There are shortcuts you can take. So for instance, if I wanted to solve this for r, right, I can trade places with these two, right? So if I have a single denominator and a single item on the opposite side, right, essentially I'm multiplying both sides by r squared and then dividing both sides by force, but in practice I'm just trading places with this. So I can take a shortcut and say, well, this must be r squared is equal to k q1 q2 over the force electric, and then I can get rid of my square by square rooting both sides, and I'm left with r is root k q1 q2 over force electric. So just rearranging these is good practice, and I encourage you to do this even when you have numbers, to rearrange the equation first and then plug in numbers, so it makes the math easier. So when you're plugging things into the calculator, and it's a good practice to get into so that you get comfortable with these things. You will be asked to come up with the equations or come up with formulas for things, and usually it's just combining things together. So a good place to start usually with these is to start at some base conservation principles. So energies, well, all energy, total energy is conserved. In some systems, mechanical energy is conserved, so that's a good place to start. Momentum is always conserved, so we'll have linear momentum and angular momentum. Charge is conserved, so I must have the same amount of charge after as before. So if you can start at some conservation point, that's a good place to start, and then start organizing your thoughts. And the idea is that you shouldn't be trying to plug formulas in first. You should be thinking about what is a relationship that you can use to then go and plug formulas in. So I encourage you to think about that. So let me go through one example that was actually an AP test question a couple of years ago, and I thought was was challenging to do it on test, but it is a fair question. So if you have something that's going in a circle, we can describe that circular motion. So that centripetal force that must make that go is equal to mass times centripetal acceleration. If this is it's going in a circle at a constant speed, then centripetal acceleration will be my tangential velocity squared divided by the radius. And if these are planets, so if this is like the moon going around the Earth, there's the Earth, that the force that's holding this together is actually gravitational force, which we describe as the product of the two masses divided by the radius squared. So the question was for you to come up with an equation that describes velocity and only has the mass and the radius in there. So so what you'll be asked to do is you'll be asked to come up with an equation that contains only constants and what they tell you it can have. So constants, so anything that's on your formula sheet on the first page. Capital G, so a gravitational constant, lowercase g, so for acceleration due to gravity here on Earth, K for our electrical constant. Be careful though, K can also mean spring constant, and that is not a universal constant. That's different for every spring, so you have to know the context that you see the letter. We just ran out of letters there. So, so in this case, I want to mash these together and try to come up with something that only contains the mass of the Earth and the radius and the universal constants. Right? So I'm trying to mash this together and get rid of everything else. So the place that I'm going to start is with the concept that my centripetal force, the thing that allows this to go in a circle, must come from gravity. So I'm going to start with this concept. My centripetal force is going to be my force of the gravity. Always there's some concept or position you have to start with. Oftentimes it's a conservation, so conservation of energy or something. But in this case, you had to recognize that the reason this goes in a circle is due to gravity. So, and now I'm going to plug in things. So I'm going to plug in what I know. So I know my centripetal force is mass times centripetal acceleration, and this is going to be the mass of the planet. And this is going to be equal to the force of gravity, which is my gravitational constant times the mass of the planet times the mass of the Earth divided by r squared. Okay. So it's looking a little more complex, but let me think about this. So mass of planet shows up on both sides, so that's going to go away. That's good because I needed to get rid of it. R shows up, and that's okay. I've got G, so I mean, G seems fine. But I have acceleration, centripetal acceleration, and that's not allowed to be. I don't want to get rid of that. So I'm going to hunt around, and this is all these three equations are given on the formula sheet. So I'm going to look at the formula sheet and say, well, look, I can replace centripetal acceleration with v squared over r. This is going to be equal to g mass of the Earth over r squared. A few things. So I'm trying to get the velocity. That's good. G is fine. Mass of the Earth is fine. Radius is fine. So now I'm just going to simplify it. I'm going to solve for velocity. So notice r shows up in a denominator on both sides. So when I multiply both sides by r, I'll cancel the square and get rid of that. And then I can take the square root. So I'll end up with v is going to be root g mass of the Earth over r. And this is the final answer. So oftentimes you end up with something which is clean. So and it's kind of satisfying to work through and discover a really simple formula that describes the velocity of something that's in orbit due to gravity. And that's a shortcut that now you know. So you can get there though. All of these are on the formula sheet. And the key to this was starting here and then working your way through until you got rid of the things that you didn't want there. I mean, these sorts of questions are going to come up, and I'll try to get you some practice with these. I think there's some practice questions that are posted. Encourage you to go through those and think about them. But this is often an area of discomfort with students, and the best way to get undiscomforted with it is to do a little bit of practice. So I hope that helps. Bye.